Howdy, and welcome to this example problem that lets us learn something about the acceleration vector. So in this example problem, we have the coordinates of a bird flying in an xy plane that are given by two equations. The first is giving the bird's direction or the bird's position in the x direction. X of t is equal to alpha times t, where alpha is equal to 2.4 meters per second. And the bird's position in the y direction is given by the second equation, y of t is equal to 3 meters minus beta times t squared, where beta is equal to 1.2 meters per second squared. So the first thing that we're interested in doing is sketching the path of the bird as it travels as time goes from t equals 0 to t equals 2 seconds. And so you can see here that I've drawn the xy plane, the xy coordinates, and I can calculate the position of the bird in both the x and y values at time t equals 0 and times t equals 2 seconds. So at time t equals 0, x of 0 is just 0 because x of t is given by alpha times t, and y of 0 is equal to just 3 meters. Then at time t equals 2 seconds, x of 2 is equal to alpha times t, which is 2.4 times 2, or 4.8. And y of 2 is equal to 3 minus beta times t squared, which is 1.2 times 2 squared, which is equal to negative 1.8 meters. So I can then take these 2 points, 0, 3 for time t equals 0, and 4.8, negative 1.8 for times t equals 2, and I can plot them on the xy plane. So you can see I have the time, I have the position for time t equals 0 located on the xy plane, and then the position for time t equals 2 in the xy plane. And so you can see that the bird is basically traveling in a southeasterly fashion, or down and to the right in the xy plane. We're then interested in calculating the velocity and acceleration vectors of the bird as functions of time. So this requires us to use a little bit of calculus, derivative calculus, in order to calculate the velocity and the acceleration vectors as functions of time. So of course, velocity in the x direction is just the derivative of x with respect to time, and velocity in the y direction is just the derivative of y with respect to time. So if we look back at our x and y equations, x is equal to alpha times t, so the derivative of x with respect to t is just alpha. Likewise, y is equal to 3 minus beta t squared, so the derivative of y with respect to t is just negative 2 beta t. So the velocity vector is just the x and y components added together. So the velocity, and the vector velocity, is equal to alpha I, that's the velocity in the x direction, plus the velocity in the y direction, which happens to be negative 2 beta t. And so in our velocity vector, that becomes negative 2 beta t j hat. So the velocity vector is just alpha I hat minus 2 beta t j hat. Likewise, to calculate the acceleration vector, that's just the derivative of velocity with respect to time. So the acceleration in the x direction is just dvx by dt. Well, vx is just alpha, so the derivative of dvx, or the derivative of velocity with respect to time, is just equal to 0. There's no t in v of x, so it's just the derivative of a constant, which is equal to 0. The acceleration in the y direction is dvy by dt, and the derivative of negative 2 beta t with respect to time is just negative 2 beta. So the acceleration of y is just negative 2 beta. So the acceleration vector would be the acceleration in the x direction plus the acceleration in the y direction, but since the acceleration in the x direction is equal to 0, the acceleration vector for this case is just negative 2 beta j hat. We're then interested in calculating the magnitude and direction of the bird's velocity and acceleration at time t equals 2 seconds. So now we use the result from our velocity and acceleration vectors to determine the magnitude of our velocity and acceleration at time t equals 2 seconds. So we're just calculating v of x at times t equals 2. But since v of x is just equal to alpha, it doesn't really matter that we're at 2 seconds. The velocity in the x direction is always the same. It's just alpha. So the velocity in the x direction is just 2.4 meters per second. The velocity in the y direction is negative 2 beta t. So the velocity in the y direction at 2 seconds is negative 2 beta times 2, which is equal to negative 2 times 1.2 times 2, or negative 4.8 meters per second. Now we have a velocity in the x direction and a velocity in the y direction, so we can calculate the magnitude of velocity at times t equals 2 by just doing our summation of the squares, the root mean square calculation. So the velocity magnitude becomes the square root of vx squared plus vy squared, or the square root of 2.4 squared plus 4.8 squared, which after doing all of the math, you'll calculate the velocity magnitude at 2 seconds to be 5.4 meters per second. To calculate the direction of the vector, we have to take the inverse tangent of the velocity in the y direction divided by the velocity in the x direction. And so the inverse tangent is negative 4.8 divided by 2.4, which gives us a value in radians, which when we convert that to degrees is 63 degrees. We use the knowledge that the velocity vector in the y direction is negative and the velocity vector in the x direction is positive. That means that we're going to be moving to the right and down in the plane. So the 63 degrees is oriented 63 degrees down from the horizontal positive x direction, which I've shown here as this reference here, where this is our x-axis and the direction of the velocity vector is 63 degrees down from that x-axis. Likewise, we can calculate the magnitude and direction of the acceleration vector. So ax is equal to 0. We've already calculated that earlier when we determined the acceleration vector in the x direction. And the acceleration vector in the y direction is just negative 2 beta. It doesn't have a time dependency. So this is negative 2 times beta, which is 1.2, which is equal to negative 2.4 meters per second squared. Likewise, we can calculate the magnitude of acceleration at 2 seconds by doing our root mean square calculation, which is just ax, the square root of ax squared plus ay squared. But since ax is equal to 0, it's just the square root of 2.4 squared, which is simply 2.4 meters per second squared. So the magnitude of our acceleration at times t equals 2 seconds is 2.4 meters per second squared. Now in this case, we would go to calculate our inverse tangent, and of course we would find that we have the limit, since we're taking a number and dividing it by 0 to calculate the inverse tangent, which based on trigonometry, that simply means that our theta is orthogonal to the x-axis, or 90 degrees. And because our y direction is downward, it means that our theta is 90 degrees down from the horizontal x direction. And again, that's because the ay acceleration vector is negative. So the last thing that we're interested in knowing is if the bird is speeding up, if it's slowing down, or if its speed is not changing, and whether or not the bird is turning, and if it is turning, in what direction is it turning? Well, in order to answer this, we simply look at the values that we've already calculated. And what we know based on our calculations is that in the x direction, the bird's velocity is not changing, since ax is equal to 0. And so the velocity that we calculated before, v of x, is just 2.4 meters per second. And because it's positive, it means that the bird is generally flying in the right-hand direction in our xy plane. In the y direction, however, the bird is moving down the y-axis. Its velocity is negative. We calculated that before with the negative 4.8 meters per second. Further, ay is non-zero, and it has the same sign as vy. In other words, the acceleration in the y direction is negative, just like the velocity in the y direction is negative. So the acceleration in the y direction is negative 2.4 meters per second squared, and the velocity in the y direction is negative 4.8 meters per second. So because the acceleration has the same sign as the velocity and the acceleration is non-zero, it means that the bird's velocity is accelerating in the negative y direction. And so the bird is speeding up in that downward motion in the xy plane. And so if I were to draw what the bird's trajectory, what its position would look like if time were to go on, we have our original trajectory here based on time t equals 0 seconds and time t equals 2 seconds, but the bird is accelerating in the y direction and turning down to the right. Okay, so the bird is turning to the right from the bird's perspective.